Welcome to The Explainer. Today, we're diving straight into a masterclass on a totally fascinating, kind of hidden world. You know, when you stand on a platform and watch a sleek, modern train glide perfectly to a stop, it's incredibly easy to think of the whole railway as just one giant automated machine. You see the glowing signals, the automated doors, the digital displays, and it really feels like technology is doing all the heavy lifting. But beneath that digital surface lies a deeply complex, resilient system powered not just by circuits, but by human beings. So today, we're going to explore the operational staff, the rigorous framework of rules they follow, and the immense responsibility they bear to keep the network safe. I really want to start right off the bat with this stark statement: machines don't keep railways safe. People do. We so often mistake the tool for the craftsman, right? While an interlocking computer or an automated train protection system will certainly stop a train from making a conflicting move, it's actually a human operator who tells that system what the operational intent is in the first place. And more importantly, when those highly advanced systems break down, fail, or lose power, it is the human operators who have to step in and manually prevent disaster. Okay, let's dive into this. Here is our roadmap for today. We'll cover 1. The human elements, 2. Key operational roles, 3. The rulebook, 4. Fundamental safety principles, 5. Degraded mode operation, and 6. The ultimate safety net. Section 1. The human element. Because despite all those high-speed trains and automated tech, safe operation unequivocally depends on competent staff. Moving right along to Section 2. Key operational roles. To really grasp how this all works, we need to meet the people at the controls. We're going to look at 3 primary roles that manage this huge, complex web of transit infrastructure. First up, we have the signaler, sometimes called the operator or dispatcher. They are literally the central nervous system of the railway. The signaler sits at a control center and inputs instructions into the signaling interlocking. They monitor the train describer systems to know exactly which train is which, and they set the routes. Now sure, the computer checks to make sure the route is safe, but it's the signaler who actively manages the flow, deciding who goes where and exactly when. Next is the driver. The driver executes the actual physical movement. They're on the front line. Their job is to operate the train's controls, but crucially, they are responding to what we call movement authorities. These authorities might be a green light on a lineside signal, an electronic display inside their cab, or, in certain tricky situations, a direct verbal order. The driver's constantly monitoring speed limits, braking curbs, and line conditions to make absolutely sure the train stays within the safe envelope provided to them. And then, we have the controller. Think of it this way. If the signaler is moving individual pieces on the board, the controller is looking at the entire board from above. They orchestrate the broader, macro-level operational flow. If a train breaks down, the controller manages the incident. If engineers need to go out onto the tracks to fix a broken rail, the controller authorizes what's called a track possession. That's the complete stoppage of normal train movements in that specific area to protect the workers. Now, what's really interesting about this is the sheer visual complexity of the interfaces these operators use. A signaler in a modern control center doesn't just look out a window anymore. They are monitoring incredibly dynamic digital displays showing exactly where trains are, how the tracks are aligned, and managing vital safety logic, all from a highly advanced digital nerve center. But here's the catch. Despite all those massive digital screens and high-speed fiber optic networks, operations still frequently boil down to humans, on the ground, communicating directly. Whether it's a shunting move in a complex yard or an engineer relaying crucial info about track conditions, the railway relies heavily on direct, precise, verbal communication between operators and the crews out on the ballast. Which brings us to Section 3, the rulebook. All of this activity, from the high-tech digital control center to the static-filled radio in the rail yard, is governed by a rigorous regulatory framework, the rulebook. And let me be clear, this isn't just a set of handy guidelines. It dictates safe operations under literally all conditions. It is the absolute law of the railway. These rules completely strip away ambiguity. When you're dealing with thousands of tons of metal moving at incredibly high speeds, you simply cannot rely on intuition or guesswork. The rules are established to ensure that every single movement is handled with an ironclad protocol. Section 4. Fundamental safety principles. The entire signaling system, and honestly every rule written about it, is essentially just trying to guarantee 4 basic pillars of safety. First, safe spacing, ensuring a train is given a route that is absolutely clear of other trains so they don't collide. Second, no excess speed, making sure the train operates within the safe braking and physical limits of the track so it doesn't derail. Third, route holding, meaning once a driver is given a green light, that route cannot be suddenly changed or revoked while the train is actually moving over it. And finally, no conflicting moves, ensuring you never authorize two trains to cross paths at the same exact time. A failure in literally any one of these pillars leads to disaster. When the system is healthy, these principles govern operations beautifully. You have track circuits constantly detecting exactly where trains are, interlockings automatically preventing conflicting moves, and digital signals issuing clear authorities. This is what we call normal operation. It's safe, it's highly efficient, and it allows for massive, high-capacity transit. But here's the big question. What happens when that digital safety net just falls away? What happens when the screens go blank, when the sensors fail, or when the physical track itself is compromised? Well, this is the most dangerous, high-stakes scenario on the railway, and it brings us to the climax of our explainer. Section 5. Degraded Mode Operation. When those automated safeguards break down, the system reverts to what's known as degraded mode. This requires intense, direct human control to keep the trains moving safely. And this isn't just theoretical. It happens all the time due to totally unpredictable real-world events. A track circuit might fail to detect a train just because of poor wheel-to-rail contact. A local power grid might go down. You might have intrusive maintenance requiring systems to be bypassed. Or, surprisingly common actually, someone might steal the copper signaling cables right off the tracks. Suddenly, the signaler can no longer see the trains on their screen and all the signals drop to red. And this brilliantly illustrates a massive shift in responsibility. Under normal operation, you have automated, system-issued movement authorities. The computer calculates the braking curves, it sets the lights. But in degraded mode, we shift entirely to intense human intervention. A signaler must manually verify that the track is clear, often relying on other staff to physically check, and then issue verbal protocols to the driver to pass a red signal. The risk profile just skyrockets. There is a very real golden rule in railway engineering. Without communications, trains cannot move. I really want to emphasize this point. When the signaling system fails, verbal communication becomes the only way to safely authorize a train to proceed. A simple radio or telephone literally replaces a multi-million-dollar digital interlocking. Because of this immense risk, operators cannot just casually chat on the radio. They have to use incredibly rigid voice protocols. Standard terminology is absolutely vital to compose these verbal messages and reduce any risk of misunderstanding. A signaler and a driver will use strictly formatted sentences, and the receiver is actually required to repeat the message back verbatim. They do this because a simple misunderstanding over a static-filled radio, like confusing line clear with line not clear, could result in a catastrophic collision. The spoken word literally becomes the safety system. Which brings us to our final part, Section 6, the ultimate safety net. We spend billions of dollars designing fail-safe computers, but the true fail-safe is the human being making critical decisions under intense pressure. Consider a simple yellow lineside telephone. When the advanced radio networks drop out, or when the in-cab displays go completely dark, a driver might literally have to climb down out of the train, walk onto the track, find one of these phones, and talk directly to the signaler. This physical hardware provides critical communication links when other systems fail. It bridges the gap when the modern world breaks down. So why does this matter? What you really should take away from this is that human error during degraded mode is the single greatest risk to railway safety. Because that technological safety net is gone, a misinterpretation of a verbal message, a momentary lapse in concentration by a signaler, or a driver misjudging their manual speed limit directly bypasses all protection. The staff ends up carrying the entire weight of the train's safety right on their shoulders. So, as we push for more and more automation and these systems become increasingly complex, I want to leave you with this provocative thought. Are we prepared for the immense responsibility placed on human operators when those systems inevitably go dark? Can we ensure that the people behind the screens remain competent, focused, and resilient enough to catch us when the computers fail? It's a question every single transit network has to constantly answer. Thanks for joining me on this explainer, and I'll see you next time.